When I say joint, you might think of your own joints, such as your knee, shoulder, elbow, or ankle. To an engineer tasked with dynamics, such as myself, a joint is an umbrella term for a fastener of components. So yes, this might include your own joints, but think bolts, screws, glue, tape, welds, friction, you name it. A joint is an entity that adjoins two components by holding them in some form of kinematic relation. Most engineers who are tasked with modeling and vibrational behavior of a machine don't particularly like joints. See, when joints connect components, they tend to change the vibrational behavior of the entire system. That change is often significant, is unavoidable, but more importantly, it's hard to model. In other words, like so many things in life, we don't like joints because we don't understand them. In numerical design, we like to make models by summing up the physical mechanisms we know take place in a system. We tell the computer which physical phenomenon we expect, and it makes us a model. This is great when the structures are simple or are dynamically well behaved, but it becomes hard when we don't know what kind of behavior to expect. Fortunately, there's also the experimental way to model. It's called system identification. We identify a system by actuating it with some force and measuring its response. Since we know the force we put in and the response we got out, we can say something about the dynamic behavior in between. If we do this at multiple locations, we tend towards a full description of the system. The joint is a special case, however. Since its defining property is that it connects two dynamic components, the joint is really a system in a system. The added difficulty here is that we must isolate the joint from the rest. To do this, we need dynamic substructuring. Dynamic substructuring, or DS for short, is the art of coupling and decoupling dynamic components to and from each other in a process not unlike addition and subtraction. For example, in the case of our little turbine blade, if we know the models of both the blade and the disc, then we can subtract them from our system measurements and isolate the joint behavior. In this way, we can obtain a joint model in the context of this setup. If the joint is simple enough, we can even transfer it to other systems. The last part also hints at the problem. Even though we do indeed remove the dynamics of the components, we see that the identified joint models are not always transferable to other systems. To explain, let me zoom in on the joint. Imagine the joint as a bottleneck of dynamic information. Each lane on this imaginary highway is represented by its degrees of freedom. The more complex the joint, the more allowable motion and the more lanes it has. It's important to remember that from a dynamic standpoint, each new lane is stiffer than the last. Therefore, each extra lane becomes increasingly hard to observe independently of the existing lanes. Even worse, the stiffer the lane, the more it's affected by the effects of measurement noise. So if the complexity of the joint requires more lanes than we can effectively observe, then even though we theoretically remove the components, due to unavoidable measurement and modeling error, we can't manage to make a clean cut. That is why, even though the techniques are very promising in theory, steps are still required before we can use the methods in practical applications.